Okay, so we're trying to work out which path will minimize the action, because according to Lagrangian mechanics, that is the path that the particle will take. So we're trying to learn how do we choose x of t so that delta s is equal to 0. Well, we varied the path x of t according to equation 1, and we varied x dot of t according to equation 2. And what we've also done is we've written the last term in equation 2 in terms of the variation appearing in equation 1. So delta x dot is d by dt of delta x. So we're about to calculate the change in the action and set that equal to 0. But before we do that, let's just ask ourselves, what is the space of paths we work on? That's going to tell us about delta x, because we need to make sure that the path that we're considering is inside the space of paths that we consider. Okay, just want to motivate something. So when we talk about delta x, what are we talking about? Well, we're at some fixed time, and we're talking about what we have to add to our classical path to get the new path. So, for example, if I look at this red wiggly path in the figure and the blue path, this is delta x. Delta x is negative. That's what I'd need to add to the blue path to get the red path. Here's another example. At this time over here, delta x is positive. I'd need to add all of that to get to the red path. Over here, it's also positive. Over here, it's also positive. So these green lines that I've drawn in the figure, this is telling you the delta x. So this is the delta x that I need to add to the blue path to get that red wiggling path. Now, one of the things that you will notice is that all of the paths that I consider start at position xi at time ti, and they land at position xf at time tf. So all of these paths coincide at the initial time and the final time. And if those paths all coincide, it means delta x, which is this interval linking the path and the other path, vanishes. So delta x has to vanish at the initial time and at the final time. So I get one more condition, which is that delta x at the initial time vanishes, as does delta x at the final time. So this is an important equation. In fact, let's call this equation 3, and let's call this equation 4. Good. Okay, so we know what space we're working on, space of paths. We know exactly how the paths are varied, and so we can go ahead now. We want to calculate what is the change in the action delta s, and then we want to set delta s to 0, because that's the path that's going to minimize the action. Okay, so now let's work out what is the change in the action. Okay, so delta s, this should be equal to integral from ti to tf dt. And then we've got L of x plus x dot. So plus delta x, and then x dot plus delta x dot. And we want the change in the action. So let's subtract off the value of the initial action. Okay, very good. Now what I'm going to do is I'm going to use the Taylor expansion to rewrite this term. Okay, so I'm just going to use Taylor expansion on the term that I've underlined in red. So what do I get? Well, I will get, this is an integral dt from the initial time to the final time. So the first term is just L of x and x dot. Then I've got plus delta x dl dx plus delta x dot dl dx dot. So that's the first order Taylor expansion. We're just working to first order because it's to first order that delta S is 0. And then we'll subtract minus from the initial time to the final time dt L of x and x dot. So we immediately see one nice simplification, which is that this term over here cancels against that term over there. Good. Now, I'm going to rewrite this as an integral from Ti to Tf dt. We've got delta x dl dx plus, and now I'm going to write this as d by dt of delta x and dl dx dot. And in doing this, what have I used? Well, I've used this equation 3. So I've just written delta x dot as d by dt of delta x. So to do this, I used 3. Good. Okay, so next, what is this equal to? Well, this is equal to an integral from Ti to Tf dt. Then we've got delta x dl dx. I'm going to do a little manipulation here. I'm going to say plus d by dt. Now, d by dt does act on delta x, but I'm actually going to take d by dt of delta x times dl dx dot. And that's not correct because d by dt acts on delta x. Good, that gives me a term on the previous line. But I'm also going to have a term where d by dt acts on dl dx dot. That should not be there. So let me subtract it out. So I'll say minus delta x d by dt of dl dx dot. Okay, so I hope that you can see that there is an equality between this term underlined in yellow on this line and the sum of these last two terms on the next line. So why did I do such a rewriting? Well, two reasons. First of all, you can see that now the first and the third terms are proportional to delta x. So that's going to turn out to be useful. And secondly, this total d by dt term, well, I know how to integrate that. So let me now just collect the terms. So what have we got? Oh, so this was here from the previous lecture. Let me just remove that. That's now gone. Okay. And now we've got an integral from Ti to Tf dt. We've got delta x. And now I'm going to collect. Here's the first term. It's delta x dl dx. And the last term is delta x times by minus d by dt dl dx dot. So that's the first and the third term. And then I need to add this term that's a total derivative, but I can immediately integrate that total derivative. So this is delta x times by dl dx dot. And I need to evaluate it at Tf minus the same thing evaluated at Ti. Now, remember what we said. Look at equation 4. We said the variation delta x vanishes at the initial time and it vanishes at the final time. So in fact, this last term over here, this term is equal to 0 by equation 4. So I don't even need to worry about that term. So what do I have now? Well, this is just the integral from Ti to Tf. It's an integral dt. Then I've got delta x times by dl dx minus d by dt of dl dx dot. Good. Okay, so what is this equation saying? Well, we have to think a little bit. We've got an integral dt of delta x times by something. Now, what is delta x? Well, in fact, this change in the action, so this is delta x, delta s. Delta s should be 0 no matter how we vary the path. So if we think about all of the variations that we could have, for these paths shown here, certainly delta x is different. So delta x is different for the red path, for the wiggling red path than it is for the straight red path. So for example, for the straight red path, this would be all of the delta x's, completely different. And I could consider some other path. So if I consider this path, for example, the first yellow path, now delta x is always negative. So for this path, all of the delta x's are less than 0. For this path, let's call this 2, all of the delta x's are greater than 0. And for this path, delta x keeps changing. So if I look at all of the possible paths that I could consider, well, delta x can be an arbitrary function. So this delta x sitting here, you should take this as an arbitrary function. Because this integral vanishes, whatever it is in the square brackets times an arbitrary function, the integral of that vanishes, it means whatever is inside the square bracket has to vanish, okay? So we now set the L dx equal to d by dt dl dx dot. So let me just stress again a very important point. We did not come to this conclusion because the integral vanished. There are plenty of functions that integrate to 0 but are not 0. We reached this conclusion because delta x is an arbitrary function and the integral is 0. This equation that we've just obtained is called the Euler-Lagrange equation of motion. And it is the basic equation of Lagrangian mechanics. Okay, we'll continue in a moment.